Section 6.6, solving equations with rational expressions. Now in this section we're going to go back to an idea that we had in chapter 2 when we were solving simple linear equations. This may be the very example that I used back in chapter 2. If not, it's close. And I showed you that we could work a problem like this leaving the fractions in place, or we discovered we could clear the fractions from this equation multiplying both sides by the LCD of all the little fractions. I also told you at that time, get used to clearing the fractions, get comfortable with it, because there will come the day when we no longer have the option, and that day has arrived. To clear the fractions from this equation, we multiply both sides by the LCD of all the little fractions. Least common multiple of 2, 4, and 6 is 12. We'll distribute that 12 here on the left-hand side. We'll simply multiply there on the right. I'm going to cross-cancel on the fly. Here we go. 12 times 1/2 x. Half of 12 is 6. So that'll leave me 6x. Plus 12 times 3/4. 12 divided by 4 is 3, times 3 is 9. On the right hand side, 5 6 times 12. 12 divided by 6 is 2, times 5 is 10. So we've cleared the fractions from this equation, and we continue in the usual manner. Subtract 9 from both sides. Subtract 9 from both sides. And divide both sides by 6. Divide both sides by 6 to find our solution, 1/6. And of course we can plug that back in to check to see that it does give me a true statement. In this section I want you to get used to checking. So let's go ahead and check this one. Let's plug back in and see if it is true that when x is 1/6 that this original statement comes out correct. So 1/2 times 1/6 is 1/12. I'm going to need twelfths for my common denominator. 3/4 becomes 9/12. That's a total of 10/12. And 10/12 reduces to 5/6. And so that checks. I don't usually insist that we check our solutions, but in this section we're going to find that checking our solutions is actually part of working these problems. We're going to start with some warm-ups. I'm going to go ahead and jump to the homework set and grab number 24. And I'm going to grab a fresh marker. I have variables and denominators. That tells me I'm working with a rational equation. And just as in that previous linear equation I was able to clear the fractions, I want to clear the rational expressions from this equation. I can do that by multiplying both sides by the least common denominator of all the fractions involved. The only denominator is y. So multiply both sides by y, and that should clear the fractions. Distributing here on the left, y times 4y. What happens? Remember, this y is over 1. It's in a numerator. Y times 4 over y. What happens? The y's cancel. What survives? Just that 4. Plus, as I distribute to this second term, what happens? The y's cancel. What survives? Just that residual factor of 1 there in the numerator. On the other side, well, 2 times y is 2y. And now I have an equation that no longer contains any rational expressions. This turns out to be a simple linear equation. We'll simplify here on the left, divide both sides by 2 to find that y is 5/2. Let's check this one. Let's see if plugging 5/2 back in for y in the original equation gives me a true statement. 4 over y is 5/2 plus 1 over y is 5/2. Is that equal to 2? To divide fractions, we flip and multiply. This is just a complex fraction where I'm going to flip and multiply. So we've got 4 now times 2/5 plus 1 times 2/5, or we could just say 1 over a fraction is just its reciprocal, right? 1 over 5/2 just means the reciprocal of 5/2. This gives me 8/5. Remember that 4 is over 1, and plus 1 times anything is itself. Eight fifths plus 2/5 is 10/5, and 10 divided by 5 is 2. And so yes, that works. It will become clear later on why I'm saying I want you to practice checking these answers. Right now, let's do number 28. Let's clear the fractions. The only fraction is this first term. The only denominator is a 4, so obviously the least common denominator is 4. Distributing that 4 here on the left, as I multiply times this first term, what happens? The 4's cancel. What survives? 5t. Plus, and whether it's a fraction or not, we have to hit it with that least common denominator, otherwise we throw the equation out of balance. 4 times t, well, simply 4t, and equals 9 times 4 is 36. The fractions are gone, and we'll finish this off as we would any simple linear equation. Simplify here on the left-hand side, combining like terms, and divide both sides by 9 to find that t is 4. And again, I'm going to insist, let's check our answer. So, plugging 4 back in for t, does that give me a true statement? Can you finish that one off in your head? Here the 4's cancel to leave me what? 5. 5 plus 4 is 9. And so yes, that checks. Number 32. Now I have to ask, does this look at all familiar to you? Just the overall nature of the problem. Isn't that a proportion? Section 2.6. Isn't this a proportion? A fraction equals a fraction. A statement that two ratios are equal. We could do what here? We could cross multiply. And it will give us actually the same thing, and I'll show you, the same thing as clearing the fractions by multiplying both sides by the LCD. My fractions involved are halves and thirds. Least common denominator is 6. There's no distributing. There's a single term on each side. And so, as I multiply here, what happens? 6 divided by 2 is 3 times that numerator. I don't usually show the canceling because quite often we are going to be distributing. We're going to need to reuse that LCD every time we distribute, so I don't like to strike it out. But here, each one's only going to get used once, so there's no harm in showing the cross canceling. On the right hand side, 6 divided by 3 is 2 times that numerator. And then we'll clean this up. Isn't this exactly the same thing you would have gotten by finding the cross products? Cross multiplying, setting the two cross products equal to each other, sure. But remember, that only works when it is a proportion. Simplify both sides. Distribute this 3. Distribute that 2. I'm going to subtract 2r from both sides. I'm going to add 15 to both sides. And I have my answer. Again, let's check this. Plugging 19 back in for r in the original equation. That'll give me 19 minus 5 over 2. Is that equal to 19 plus 2 over 3? Well, that's going to be 14 over 2 compared to 21 over 3. And I think you can see that, yes, this does indeed check. 7 equals 7. And so that checks. Let's do number 36. Number 36, I could work as a proportion, but I want to stay in this frame of mind of clearing fractions because that's going to be much more useful to us in this particular section. So although I could use the cross products, I could cross multiply, let me do this by saying I'm going to clear the fractions. Multiply both sides. Multiply both sides by the least common denominator. I have factors of 5 and I have factors of x, each appearing no more than once in any one denominator. My least common denominator then is 5x. As I multiply here on the left, what happens? Well, the x's will cancel. What survives? That pink 5 and the black numerator. And we'll clean that up in a minute. On the right-hand side, as I multiply, what happens? Well, the 5's will cancel. What survives? The black negative 17 and that pink x. And we now have a linear equation that we can solve. Distribute that 5. I'm going to take my x's to the right this time. I'm going to add 10x to both sides. Add 10x to both sides and then divide both sides by negative 7 to find that x is negative 5. Let's check this one. Plugging negative 5 back in for any place we originally see an x, we have 7 minus 2 times negative 5 over negative 5. Is that equal to negative 17 over 5? What do I have here? That's 7 and now plus 10. And 7 plus 10 is 17. 17 over negative 5, that's certainly equal to negative 17 over 5. Those are both just what? Negative 17/5. And so that checks. Now for our next problem, I want to make one up for us. The instructions, as they have been this entire time, read, solve. Solve this equation. Find a value of x that will make this original statement true. Find all values of x that will make this original statement true. Well, let me think about it. Just looking at this looks very strange to begin with. I'm talking about some fraction that is equal to itself plus 1. Is there any number, is there any real number out there that is equal to itself plus 1? No. This right-hand side is always going to be 1 bigger. It's always going to be 1 bigger. And so there could not possibly be a solution here. Now, one way to solve this problem, I could subtract 2 over x from both sides. When I do that, that will give me 0 equals 1, which is a false statement, which tells me no solution. But instead of tackling it like this, let me work it like we've been working the previous problems, and that is, let me clear the fractions. Let me clear the fractions from this equation. Multiply both sides by the least common denominator of all the fractions involved. I have 2 fractions, and the only denominator here is x. So multiply both sides by x. We'll distribute here on the right. So, on the left-hand side, what happens? The x's cancel to leave just 2. As I distribute the x on the right-hand side, as I distribute to this first term, what happens? The x's cancel. What survives? Just that 2. And plus, as I distribute to this last term, x times 1 is just x. Now let me subtract 2 from both sides. Let me subtract 2 from both sides. And this time, instead of no solution, I get a solution of x equals 0. X equals 0. Okay, so I've worked the problem one way and it said no solution. And when I thought about the problem initially, I thought there can't be a solution. But going through it using the methods of this section, suddenly there's a solution? Actually, no. Let's check this solution. Plug 0 back in for x in the original statement of the problem. Well, what do we have? 2 over 0 is undefined. Undefined is not a number. Undefined can't be equal to anything, not even to itself. So this does not check. Which means that I have to reject this proposed solution. And since it was the only solution available to me, I have returned to the notion that this equation has no solution. Well, let me ask you, what happened here? How is it that following the algebra, I ended up with a proposed solution that turned out to not work? Well, it goes back to chapter 2. I told you at the time we would turn back to page 112 and look at this brown box again. And I said you wouldn't remember it. Maybe you do, maybe you don't. Page 112, the brown box. The multiplication property of equality. This is the property that allows me to multiply both sides of an equation by the same thing and get an equivalent equation, that is, without changing the solution set. And that's all I did. I multiplied both sides by x. But what does it say? Here in the brown box, page 112, if a, b, and c represent real numbers where c is not 0, then a equals b and ac equals bc are equivalent. That is, you can multiply both sides of an equation by the same non-zero number without changing its solution set. What did it turn out x would have to be if this were going to work? X turned out to be 0. What did I multiply both sides by? I multiplied both sides by x. I multiplied both sides by 0 without ever knowing it. That's the reason that we have to check our solutions in this section. I ended up multiplying both sides by 0, which produced an extraneous solution. So in this section, whenever you have variables and denominators and you clear the fractions, what you get are proposed solutions. But then you must check to make sure that they are viable solutions, that they do indeed work. And in this case, the only proposed solution was 0. And when we checked, we got terms that were undefined, which means we had to throw it out. Because undefined can't check. It can't make a true statement. Undefined cannot be equal to anything. It's not a number. It cannot even be equal to itself. Let's try now number 38. All right, this doesn't look too bad. We want to clear the fractions from this equation by multiplying both sides by the least common denominator. The only denominator here is a plus 5. So multiply both sides by a plus 5. We'll distribute that binomial to each of the two terms here on the left. As we distribute to this first term, what happens? The a plus 5's cancel. What survives? That negative 5. And minus, as we distribute to the second term, well, we simply have the 2 times the pink a plus 5. We'll clean that up in a minute. If I get in a hurry and distribute that 2, if I've already written my minus and I distribute that 2, I'd get what? A 2a plus 10? I'd make a sign error because you see in a minute we're going to distribute the negative along with that 2. That's one good reason not to try to do too much in one step. On the right hand side, what happens? The a plus 5's cancel to leave simply that a from the original numerator. Now let's clean this up. Distribute that negative 2. Continue simplifying by combining like terms on the left. I'm going to take my variable to the right hand side. I'm going to add 2a to both sides. And then finally divide both sides by 3 to find that a is negative 5. Now what we've learned is I'm not ready to put a box around that. I'm not ready to declare that that is my final answer until I've checked. So is negative 5 a viable solution? It's a proposed solution, but I've multiplied both sides by a variable expression. You can already see what's going to happen as we go to check this, right? When I plug negative 5 back in for A. That's going to create a problem. Negative 5 over 0. Negative 5 over 0. This does not check because I have two terms that go undefined. And undefined is not a number. It can't be equal to anything, not even to itself. So negative 5 does not check back in the equation. Negative 5 does not check back in the equation, and so I have to reject it. And since it was the only proposed solution and I had to throw it out, there is no solution. Now, honestly, when I say you need to check these problems, what you really need to check is to see that your proposed solution causes no denominator to be 0. You at least must check that much. It is not absolutely necessary to do a full check every time, but you do have to at least check to see that your proposed solution causes no problems, causes no term to be undefined. And obviously, what's going to make this first rational expression undefined? Section 6.1, when A is negative 5. Also, when A is negative 5, what did I end up multiplying on both sides of my equation? Again, I multiplied both sides by 0 and never knew it. That's why we have to check these, because we're multiplying by variable expressions. Back in chapter 2, we were forbidden to multiply or divide both sides of an equation by an expression that contained a variable, because we weren't ready for it yet. Well, now we have to. And the cost of that is having to check our solutions to make sure that they remain viable, that they cause no denominator to be 0, that they cause no term to be undefined. Now, I'm going to leave it here for now. Next time, we're going to continue in this section and really crank things up. Not only do we have more equations to solve, but if you look ahead at the problem starting with number 83, we once again are going to explore formulas. We did this back in chapter 2. We solved formulas for one variable in terms of the other. And now what we have is equations that contain rational expressions in our formulas. Remember, these are also sometimes called literal equations. In fact, you'll hear me say that more often than formulas because that's what I'm used to. So, next time we've got some big, heavy, rational equations to solve. And in addition to that, we're going to look at solving these literal equations. For now, and I'll put it on our little website, you can work problems up through number 43.